Okay guys, in this video we are going to talk about the electronic structure of atoms, and we're going to focus on the hydrogen atom first since it's easier to deal with, and then after that we'll talk about many electron atoms. So first of all, electrons are quantum mechanical particles, and so they are described by a wave function in order to represent the wave-like character of the electron. So we're going to be talking about the types of wave functions that electrons exhibit when they are confined within an atom. And as we talked about in a previous video, whenever you take a wave and you confine it in space, that ends up restricting the wavelength, and in turn that restricts the energy associated with that wave. So now we have electrons that are described by waves, and they are confined within an atom. And so we wind up with these standing wave functions for the electrons within the atom that have discretized or quantized energies. The wave functions within an atom are called atomic orbitals, and that's because they represent the motion of the electrons as they orbit the nucleus of the atom. These atomic orbitals, they have discrete energies, and they are described by a set of 4 quantum numbers. That is, the wave function for an electron within an atom is represented by a wave that can be identified by 4 distinct numbers, which are called the quantum numbers. And so we're going to review what those quantum numbers are and how these impact the wave function of the electrons within an atom. So the first quantum number we've actually already seen before. It's identical to Bohr's quantum number that we talked about when we looked at the Bohr model. The principal quantum number, n, it determines the energy of an electron within a hydrogen atom, and it also represents the size of the atomic orbital for that electron, and we call this the shell. So you can think of the atom as being somewhat like an onion in the sense that it has different layers, and the shell represents how far away the electron is on average from the center of the atom at the nucleus. So the energy and size of an atomic orbital are determined by the principal quantum number n. Now, the electron is also moving around the atom, so it's moving in a curved path around the atom. And it turns out that whenever you have something that's moving in an orbital fashion, it has something called angular momentum. And for the electronic motion, the angular momentum is quantized as well. And so there's a separate quantum number for that angular momentum, and it has the letter L. This essentially determines, as we'll see in the graphics, the shape of the atomic orbital. And so we are going to associate differently shaped atomic orbitals with this angular momentum quantum number L. And this is also called the subshell, meaning it's a part of the larger shell for a given electron. There's a third quantum number called the magnetic quantum number. The letters that we use are M with the subscript L, and you'll see why we have that subscript L in a few moments. This quantum number determines the spatial orientation of the atomic orbital, as we'll see in the graphics. There's a fourth quantum number, which we don't really need to talk about that much for at least a hydrogen atom, but when we start talking about many electron atoms, the spin quantum number becomes very important. It's represented by an M subscript S, and we're going to talk more specifically about spin a bit later in this lecture series. So we've got 4 quantum numbers that represent the type of atomic orbital that an electron can occupy, and very frequently we will refer just to the principal quantum number and the angular momentum quantum number using this subshell notation, where the combination of the n value and the L value, where L is represented by a letter, identifies what orbital we are talking about. So here are the different possible values for the quantum numbers. And it turns out that only certain combinations of the quantum numbers are allowed, in the sense that there's an atomic orbital for that particular combination. So the principal quantum number can take on values that range from 1 as the lowest value of the principal quantum number on up to infinity, okay, in steps of 1, so integers. The different values of n are associated with different electron shells, and those shells are frequently designated by letters. So the n equals 1 shell is also called the K shell. The n equals 2 shell is called the L shell, and so on. It's just alphabetical after n. The angular momentum quantum number, L, which determines the shape of the atomic orbital and identifies the subshell that the electron is occupying, its value depends upon, or the range of its values rather, depends upon the value of n. So the value of L ranges from 0, that's the lowest possible value for L, up to a value n minus 1. So for example, if n were 1, then there's only one possible value for L, and that would be a value of 0. If the electron is occupying an atomic orbital with the value of n equals 2, then the angular momentum quantum number can take on two values. It could be either 0 or 1. And for the case where L equals 0, we would say that the electron occupies an s orbital. If the angular momentum quantum number was 1, then we would say that the electron is occupying a p orbital. If you go up to n equals 3, then values of 0, 1, and 2 are possible, which means that the electron could be occupying a d-type orbital, and it goes on from there. The magnetic quantum number, m sub L, the range of the possible values for m sub L depend upon the value of L, and they range from a value of minus L to plus L in steps of 1. So if your electron is occupying an s orbital, then there's only one possible value for m sub L, and that would be 0. However, if your electron was occupying a p orbital, then the value of m sub L can take on three values. It can take on minus 1, 0, and 1. If you were on a d orbital, you could take on minus 2, minus 1, 0, 1, and 2 as the possible m sub L values. Finally, for the fourth quantum number, there's always two possibilities. Either the value of m sub s could be minus 1/2, or it could be plus 1/2. And we call the minus 1/2 case spin down, and we call the plus 1/2 case spin up. Like I said, we'll talk about spin in more detail later to try to understand where spin comes from. Right now, we mostly want to focus on the principal, angular momentum, and magnetic quantum numbers and how they work together to identify a unique atomic orbital. So what we're going to do next is enumerate the different allowed values of the quantum numbers for the first few shells of the hydrogen atom. Okay, and so I'm going to use paper to do this. Let's start with the first shell. So in the first shell, the quantum number n, the principal quantum number, is 1. And the values of L that are possible are L equals 0 only for that case. And so the way that we denote the atomic orbital, there's several ways we can denote it. We will write the orbitals as a wave function. So this psi is a function of space. So you could think of it as depending upon the Cartesian coordinates of the electron, so its xyz coordinate, or you can think of it in terms of its radial coordinate and then two angles, theta and phi, which describe the orientation of the electron within the atom. This function depends upon the three quantum numbers that we're talking about. So it's really a function that depends on n, L, and m sub L. Okay, so we use these quantum numbers to identify what function that we're talking about. Again, going back to the n equals 1 case, we have L equals 0 is possible only for n equals 1, and then when L equals 0, the only possible value of m sub L is also 0. So we would denote the atomic orbital for this combination of quantum numbers as psi 1, 0, 0. And we call this a 1s orbital. Let's talk about the n equals 2 shell. So for n equals 2, there are two possibilities for L. L could be 0, or L could be 1. For the case where L equals 0, there's only one possible value of m sub L, and that is 0. And so for this combination of quantum numbers, we have a psi 2, 0, 0, and we call that a 2s orbital. The value of 2 comes from the principal quantum number. The letter s comes from the fact that L equals 0. Well, when L equals 1, m sub L can take on multiple values now. It can take on the value of -1, or 0, or +1. And so we are going to get multiple combinations. So we can have a psi 2, 1, -1. Likewise, there is a psi 2, 1, 0. And then also a psi 2, 1, -1. Okay, so for the case where L equals 1, there are three possible values of m sub L. And collectively, these are referred to as 2p orbitals. Notice that there's three unique ways in which you can have a 2p orbital. For n equals 3, the third shell, L can take on values of 0, 1, or a value of 2. For the case where L equals 0, there is only one possible value of m sub L, which is 0. For L equals 1, again, we are going to have three possible values for m sub L, -1, 0, and 1. For L equals 2, there are five possible values of m sub L, -2, -1, 0, +1, and +2. So we're going to wind up with 5 unique orbitals for this subshell. 3 unique orbitals for this subshell, and only 1 unique orbital for this subshell. So we have a psi 3, 0, 0. That we call a 3s orbital. It's n equals 3. Because it's L equals 0, it's an s-type orbital. For the combinations where n equals 3, L equals 1, and m sub L can take on these values, we're going to wind up with a 3, 1, -1, a 3, 1, 0, and a 3, 1, +1. So these are 3 unique atomic orbitals, and collectively they would be called the 3p orbitals. For the case where L equals 2, 3, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. There are 5 unique atomic orbitals corresponding to this subshell, and these are referred to as the 3d orbitals. Okay? I'm going to go ahead and let you think about the fourth shell for hydrogen on your own and see if you can enumerate all of the different possibilities. What you want to be able to do in the end is recognize good sets of quantum numbers that follow the patterns that we've enumerated here from bad quantum numbers that would not be consistent with this pattern. And I believe in the next exercise, what we're looking at are different sets of quantum numbers, and we're being asked to sort out which ones are good and which ones are bad, which ones are not possible. So for part A, we see that we've got the principal quantum number is 1, the angular momentum quantum number is 1, m sub L is 0, and m sub s is plus 1/2. And so the question is this a valid set of quantum numbers or not? The answer in this case, it is not a valid set of quantum numbers because the value of L is too large for the given value of n. N ranges from 1, 2, and so on up to a maximum value of n minus 1. In this case, n equals 1, and so I should have written L here. In this case, n equals 1, and so the maximum value of L would be 0. So this is not an allowed quantum number. For part B, we have n equals 3, L equals 1, m sub L equals minus 2, and m sub S equals minus 1/2. Well, you can have a n equals 3 shell. L equals 1 is allowed when n equals 3. However, when L equals 1, m sub L equals minus 2 is not allowed because the value of m sub L ranges from minus L, goes through 0, all the way up to plus L. And so since L is 1, you're only allowed to have an m sub L value of minus 1, 0, and plus 1. Okay, so this is not allowed. For part C, we have n equals 2, L equals 1, m sub L equals 0, and m sub S equals plus 1/2. This would be an allowed set of quantum numbers. You can have an n equals 2 electron. In that case, L is allowed to be 1. M sub L equals 0 is allowed when L equals 1. And then the electron can have a plus or minus 1/2 spin quantum number. Okay, and so that's an acceptable value. For D here, n equals 2, L equals 0. That's fine, there's nothing wrong with that. M sub L should be 0 when L equals 0. However, m sub S equals 1, that's not one of the valid quantum numbers for m sub S for an electron. Okay, so part D is an unacceptable set of quantum numbers because it doesn't have the right value for m sub S. M sub S should be plus or minus 1/2. I believe I have another set. I'm going to go ahead and go through these just to illustrate what's going on. So here for part A, n equals 0, L equals 1, m sub L equals 0, and m sub S equals plus 1/2. This is a bad set of quantum numbers because n cannot take on a value of 0. N ranges from 1, 2, 3, on up to infinity. So n equals 1 is not one of the allowed values, so this is not a good set of quantum numbers. For part B, n equals 2, that's fine. However, L equals 3, that's no good. The maximum value of L is n minus 1. In this case, because n equals 2, you're allowed to have a L value of 0 and 1, but not 3 or higher. Okay, so B is a bad set of quantum numbers. For part C, n equals 3, L equals 2, m sub L equals plus 3. You probably picked up on the error. That's not allowed. Since L is equal to 2, m sub L can take on values from negative 2 to 2, and so plus 3 is out of the acceptable range for this particular subshell. For part D, n equals 3, L equals 2, that's okay. M sub L equals plus 2, yes, that's allowed. But m sub S equals 0, that's not one of the allowed values of m sub S. M sub S can only be plus or minus 1/2. Okay? So this is something that you need to be able to do for the assessments. You need to be able to distinguish good sets of quantum numbers from bad sets of quantum numbers. I'm going to go ahead and stop this video here, and we'll talk about the quantum numbers in more detail in the next video.